Hi there everyone. What I want to do in this first recording is just run through a quick revision of the standard linear regression model and make sure that we know what we're moving from. So we're then going to move on, after we've looked at the linear regression model, to what we call generalized linear regression models, and that's really the basis for all of the work that's going to follow. So let's just recall what we have, and the reason for reviewing this is just to remind ourselves that we are quite familiar with the log transformation already, and really that's going to be something that we're playing around with, just different ways of implementing that kind of transformation. So we say we know about linear models, we know about log linear models when we say we put a log transformation on the dependent variable, and what we realized then was it just changed the interpretation of the slope. So really simple sort of setup. If you transform something here, it changes the interpretation of the slope. We could also put the log transformation on this side, and that's something just to know that, we've done this before. We know we've put log transformations on the x variables, and again, we just saw that it changed the interpretation of the slope. And the final one that we really looked at was really this log model. Now, what do we kind of see? What would be an example? So we know that when we say linear regression, we don't mean that we're fitting a straight line. Here is some data. We've got two variables. One is height above sea level, and one is a diversity index measure. I think this is actually a Shannon index. I can't recall exactly. So we've got something like this. So this is clearly not a straight line, yet we use linear regression for non-linear curve fitting. Okay, so that's a slight difference in the language. We still have curves, and we use the term linear regression to fit those models. How did we go about it? So here's an example. You can see that one of the ways we explored these things was we just sort of put the different transformations on and looked at what kind of scatter we got for the data, and then based on that we picked one that was plausible. And recall that we weren't really often saying one was better than the other, just that many possible models are plausible. We're going to pick one that is plausible. In this case, I picked a log model, and I've got my little summary here. And so we know that this slope coefficient, when we've got a log model, we'll be saying a 1% change in altitude on average leads to a 2.7% decrease in the diversity index. So we got quite comfortable with doing those sorts of things. The next extension, and the way we would sort of finish that up, is with a nice plot of our data. So kind of clean it up a bit and put a legend in it. Again, the raw data is not a line, it's clearly non-linear, but we put some transformations on it, and that allows us to use the models that we are familiar with. And that's really a recurrent theme about what we're doing here. We're just transforming some data a little bit and fitting some models that are like that. Now, all of that generalized, okay? So we can have a dependent variable, and we can have as many of these variables on the right here as we want. We can have continuous variables, or we can have factor variables. It doesn't matter, but you can start to see this sort of general notation. You've got up to k explanatory variables, and you can have squared terms or all sorts of things in there. So our simple model generalizes, and that's also going to be true when we look at generalized linear models, that we can have many covariates on the right hand side. So we look at something that we can still visualize here. We have generalized to two explanatory variables. Y is equal to an intercept, a slope in x1 and a slope in x2, and I have a specific case here, which is a measure for some skiers on acid in the body, and how it relates to age and how it relates to weight. And what we can do is, if we read in that data, so we've got three variables, again, still linear regression models. This is the extent to which we can visualize things. We can see here, if we plot the data, we have my acid measurement running along the vertical, we have age running this direction, and weight running this direction. I've tried to shade and put some perspective on here so you can see what we're doing. And then when we move on to our model, I found that the log fitted well, and I have age and weight. So the acid is going down as you get older and going up as you become heavier. And in these cases, that weight is really muscle mass. These guys are, it's conditional on these guys being fit guys. Okay, and then we can look at our plot. So you can see here sort of that what we're doing is fitting in a plane. So what you can see is as we go down here, this line is actually going down. So that's our negative slope for age, and in the weight axis, it's going up. So I've got my measurements going up in the weight, and you can see here going down with age. So what am I doing? I'm fitting a plane. So just if you can keep that in mind, that after this sort of three-dimensional plot, so 2 explanatory variables and 1 dependent variable, we can't really visualize what's going on, but it's really this idea of fitting a plane into the however many dimensions that we're working with. So that's a bit of a wrap up on a quick bit of revision that we've done, and that's a good place to pause.